Welcome to Unit 5, Day 3 for Oak Ridge Level Chemistry. So, a few quick reminders before we begin. You should be checking your grades often right now. We're almost at the end of the semester. We want to help you get the grade that you want to achieve. So be looking at student access and be in communication. There are ways to pull your grades up. We have retakes as a possibility and also our extra credit module. Please make sure you get in touch with your teacher for more information about any of that. Okay, on to our notes. We're going to talk about predicting products of combustion, and we're also going to learn how to identify oxidation and reduction reactions today. So, to predict products of combustion, you want to basically be looking for a hydrocarbon, which is going to be your C's and your H's. Okay, any compounds. So where you see the number sign, it could be any number down there. It could be 2, it could be 6. They'll change. What won't change is the rest of the equation. So some combination of hydrocarbon plus an oxygen will yield you carbon dioxide and water. So CO2 and H2O are always the products, always of combustion, every single time. So you will know a combustion reaction has occurred if you see CO2 and H2O, and we will definitely test you on that. So be very familiar with this kind of setup. That's how you are going to be predicting a combustion reaction. Look for those CHOs, or as we call it, CHO. CHO order is what I always tell my students, because unlike last time where I said it didn't really matter which you started with, for combustion reactions, it does matter. We always solve them in CHO order or CHO order, meaning you have to start by balancing the carbons, then you're going to balance your hydrogens, finally you're going to balance the oxygens last. So let's take a look. We're going to switch over to the document camera. Here we go. We're going to solve in CHO order. I'm going to start with my carbons. Remember, change that arrow to an equal sign because the left and the right sides are equal. On the left, I have 2 carbons. On the right side, I have 1. So I'm going to change this by putting a coefficient of 2. So now on each side, I have 2 carbons and 2 carbons. All right, now let's go to H, CHO order. On the left side, I have 6 hydrogens. On the right side, I have 2. So I need them to both be 6. So I'm going to put a coefficient of 3 in there because 3 times 2 is equal to 6. Now we're each at 6 and 6. And this is where you have to really be paying attention because the oxygen is what is tricky about a combustion reaction. So, left and right sides, let's take a look. On the left side, we have 2 oxygens. I'm just going to record that total now. Now, on the right side, you have to be paying attention because I have 2 times 2, which equals 4, but I also have some oxygen over here. So I've got 4 plus 3 times 1 oxygen, because remember, coefficients go everywhere. 4 plus 3, so that is equal to 7. Now, this presents a bit of an issue. I'm going to go ahead and put in my coefficient of 1 right here. Because 7 and 2, the only way to make these numbers equal is to just basically multiply them together. So that's what I'm going to go ahead and do. But of course, that is going to mean that I need to update my totals everywhere else because I need this side to also now be equal to 14, which is 7 times 2. And that's just because you can't multiply. I can't say 3.5, right? Because you can't have half of an oxygen. So instead of doing that, you just can multiply them. If you end up with an odd number like this, or a number where you can't make them equal to each other, just double multiply them by each other. So I'm going to take that 7, and now I'm going to update my oxygen totals. Of course, 7 times 2 is equal to 14. Now, The easiest way that I can tell you is that you just have to double everything else as well. Everything aside from this oxygen is now going to get doubled, and that will make sure your numbers are correct every single time. So what do I mean by double? Okay, so double 1, that's 2. Remember, I'm going to leave this one alone. 2 doubled is 4. 3 doubled is 6. Now they're all going to equal out. And if you want, you can check yourself. It's not a bad idea, right? So I'm going to check, starting with my C's. 2 times 2 is 4. So I've got 4 on the left, and I've got 4 times 1 is 4. 4 on the right. Okay, now let's do our H's. 2 times 6 is 12. Got 6 on the left, or pardon, 12 on the left, and I've got 6 times 2, which is equal to 12 on the right. And then our oxygens, we have 7 times 2, which is 14 on the left. And let's check on this side. So we've got 4 times 2, which is equal to 8, plus 6 times 1, which is equal to 6, which equals 14. So we are balanced. Okay. Next problem, I'm going to do this in a different color so it doesn't look like they're running into each other. Now, you're not going to have to do that every single time, and you'll see what I mean here in just a minute. In the next example, as always, we're going to start in CHO order. So I'm going to check my carbons first. 3 carbons on the left, and I have 1 on the right, so I'm going to put in a coefficient of 3. So they're both 3. Now I'm going to do my hydrogens. Remember, they have to equal each other. On the left side I have 8, and on the right side I have 2. So I need to make them both 8 on each side, so I'm going to put in a coefficient of 4. 4 times 2 is equal to 8. So now they're both 8. And very last, I'm going to check on my oxygens. So I have 2 on the left side, and then on the right side I have 3 times 2, which is equal to 6, plus 4 times 1, which is equal to 4, and that equals 10. So I've got 10. Now this one's a lot better because I can get them, I don't have to put in a part of a number, so I can easily just say, I can put a coefficient of 5 right here, and 5 times 2 is equal to 10. So you don't always have to do what we did up above. It's only when the only way you can make it is to put in a fraction, which we did not have to do on this problem. So, moving on. CHO order. So I'm going to start with my C's. I've got four on the left, 4, and on the other side, I've got 1, so I'm going to put in a coefficient of 4, so they're both 4. Now let's do our H's. On the left side, I have 6. On the right side, I only have 2. So I need to put in a coefficient of 3, because 3 times 2 is equal to 6. We want each side to be equal in your total amount. So there's our 6. I'm going to put my 1 here. Alright, now on to our problem child. It's oxygen, always a problem. On the left side I have 2 oxygens, but on the right side I have 4 times 2 is 8, plus 3. Uh-oh, this is going to be another one of those odd number situation, because I've got 11. I can't multiply this oxygen by a fraction. I can't say 5.5 because you can't have 5.5 oxygens. So what I can do instead is multiply it by 11, and just like before, I'm just going to double everything else except for the oxygen. So I'm going to put my 11 here, and then I'm just going to double all the other columns. And that will give you the correct amount every single time. So 1 doubled is 2, 4 doubled is 8, 3 doubled is 6. And you can count them up and check, but I promise you now it is all nice and balanced. Okay. Like I said, you don't need to do this every time. If you can make it equal like we did in the previous problem without making a fraction, you don't have to. But in cases of numbers like 7 and numbers like 11, that extra step of doubling at the end is necessary. Now, you might be like, there's some stuff missing here on this next problem. I don't know what's going on. And my answer is, sure you do. Because we know every single time what the products of combustion are. Notice in all our previous problems, they have these same products. It's always some hydrocarbon plus oxygen will always give you carbon dioxide, CO2, plus H2O, plus water. And then it's just up to us to find, just like we were doing before, our C's, H's, and O's. So we're going to solve these in CHO order. Alright, so on the left side, I have 5 carbons. On the right side, I only have 1. So I'm going to put in a coefficient of 5. Alright, now let's do our H's. On the left side, I have 12 hydrogens. On the right side, I only have 2, so I need to make them equal on both sides. So I need to say, okay, 6 times 2 is equal to 12. I'm going to put in my coefficient of 6. And I'm going to put in my coefficient of 1 to keep my place. And now we're going to look at our problem child, the oxygen. Let's see if oxygen is going to be a problem for this one. Okay, I've got 2 on the left side. And in the right side, I have 5 times 2 is equal to 10 plus 6, because 6 times 1. And nope, it's not a problem this time because it's 18, which of course you can achieve that without a fraction. So I'm not going to need to do that doubling. I'm just going to think, what times 2 is equal to 18? And that would be 9. All right. Now we're going to change gears a little bit and think about oxidation reduction reactions. Okay, oxidation reduction reactions are also known as redox reaction. So redox, it's just a shortening, oxidation of reduction, just shortened. So, in an oxidation reduction reaction, electrons move between atoms. See, this is our electron. So this is a redox. So A is giving away its electron to B. So what are our definitions here? Reduction means gaining electrons in the most simple terms, while oxidation is the loss of electrons. In this picture here, A is oxidized. So, oxidation. Because A is losing its electrons. See, A is losing its electrons. B, on the other hand, is showing reduction. B is reduced because B is gaining electrons. So I know this seems counterintuitive because you're probably thinking, why is reduction gaining something? And that is a valid point. It is confusing. What is actually being reduced here is our oxidation number, though, because gaining your electrons will cause an increase in your oxidation number. So as much as that's counterintuitive, that's what's really going on. So there is an easier way to remember this, and we're going to show you that over here. All oxidation reactions are paired with reduction reactions. So they don't occur independently, and that's why we know them as redox, because one will not happen without the other. And electrons that are lost by the reactant that is oxidized are gained by the reactant that is reduced. So remember, we just finished a unit on ionic bonding. So this is a good way of thinking about that. So in ionic bonding, the electrons are transferred from the metal to the nonmetal, and that's really what we're talking about with oxidation reduction here. So electrons are lost by the reactant that is oxidized and gained by the reactant that is reduced. Okay, so remember I said there was an easier way to remember this, and that is by the kind of little memory trick oil rig. So for oil rig, oil, so oxidation, and I would write this in, is losing oil. Oxidation is losing. So losing electrons, atoms become more positively charged, and this tends to happen with our cations. So remember our cations, we said metals go meow, they're positively cute, cat paws. So these are our cations. They become more positively charged. Once they lose those electrons, they become more positively charged. So with our reduction, what is being reduced? Again, it's that oxidation number. The gaining electrons reduces the oxidation number. So if chlorine gains an electron, it won't have an oxidation number of -1. It will have an oxidation number of 0. So that's where that gaining comes from, because it's confusing that reduction and gaining are paired. But that's why I wanted you to learn this memory trick, oil rig. Oxidation is losing, reduction is gaining. Reduction is gaining. So this is gaining electrons, which will cause our atom to become more negatively charged. We're going to increase the amount of negative charge on that atom. So this happens with anions or nonmetals. Nonmetals. So maybe even write that in there. I'm going to write in metals, nonmetals. Okay. So in our little picture that we have over here, and this one, let's think. First, we want to think, is this a metal or a nonmetal? Sodium. Sodium is a metal. Okay, sodium is a metal. So sodium, if we know it's a metal, because we wrote that down up here, sodium is losing, right? This sodium is a metal, so it's going to be losing. That means it's oxidized. So this sodium is oxidized. loses an electron. Chlorine, on the other hand, chlorine is a nonmetal, and it is reduced. It's reduced because it has gains an electron, which reduces its oxidation number. So here's an example, another example of a redox reaction. Let's think. Let's look at this here, this Mg and S. Mg and S, the first thing you want to do when you're looking at oxidation reduction is think which one's the metal, which one's the nonmetal. Okay, so that magnesium is your metal. The sulfur is a nonmetal. So metals, we talked about at the beginning, metals generally, not always, but for what you need to know, metals are generally going to be the oxidized. So here, the magnesium is undergoing oxidation. The sulfur, the nonmetal, is undergone reduction. The sulfur has been reduced. Okay, here are some practice problems. Okay, the first one says, in the reaction between Mg and Cl2, which element is being reduced? Mg and Cl2. Once again, really if you can just identify which one's the metal, the magnesium, and which one is the nonmetal, that's the chlorine, then it should be pretty simple to figure out which one's being oxidized and which one's being reduced. So, just like we were looking at before, up to your oil rig, cations or metals usually are oxidized. So the magnesium is oxidized and the chlorine is reduced. Okay, once again, just identify your metal versus nonmetal. The potassium is a metal, the fluorine is the nonmetal. The metals are the things that get oxidized. That's what this question's asking. So that would be my potassium. My K, because it's the metal. It's the one that's going to lose its electrons. The metals lose them. And strontium plus nitrogen, which one is being reduced? Strontium is the metal. Nitrogen is the nonmetal. So nitrogen is going to be reduced. Reduction is gaining. It's gained some electrons. All right, here we go. This one's worded a little bit differently, but it's still the same idea. Sodium is still a metal. Okay, sodium is still a metal. And we know that our metals are oxidized. In this reaction, sodium is being oxidized. That's because in the very most basic terms, there are exceptions you can learn later if you go on to study chemistry, but in our very most basic terms, we're going to say that oxidation generally happens to our metals. They're generally the ones who want to lose electrons. Okay, so sodium is being oxidized. Because look, it's lost its electron. And generally, they'll do that when they undergo those ionic bonds. Okay, so right now we're going to start that homework packet, and we'll see you in the next video.